Hey everybody, I've been spending a lot of time on Slack lately. I see there's a lot of confusion on neural networks and maybe how to implement Q-learning with neural networks for some of the people that haven't taken machine learning or haven't taken it in a while. So I figured I could go through some of the papers and kind of put together a collection of useful material and maybe help bridge the gap between some of these algorithms in a digestible way for everybody. So first off, you need to be able to understand the tabular version of Q-learning. Since there was already an assignment on this, I'm going to assume that everyone has a pretty good handle on it. There's a couple different update rules for tabular Q-learning. I'm putting this one here just because it closely resembles the way that the neural network is going to do it. And generally, your Q, at least in the tabular version, takes in a state and an action, and it spits out the value for taking that action at that state. So when we're training, we want to move our old value, which is probably incorrect, in a small direction to improve the error, and we control how much we move it by this learning rate. And the error is calculated by using the Bellman equation to get what our actual value should be based on the sample we just experienced, and subtracting from that our old value. So the difference between what we think the real answer is minus what we thought the answer was before. So pretty straightforward. Everyone probably has a pretty good handle on that, but it's fundamental to everything moving forward. So what's a neural network? This isn't the best explanation, but it will hit the wave tops of what a neural network is. There's also many other types of neural networks. In the papers, you're going to see a lot about convolutional neural networks, which are specialized architectures for dealing with images mostly as input. And that's sort of synonymous with a lot of what you'll see when you're researching deep learning. Usually they're talking about convolutional neural networks with many layers. But what we're going to talk about here is just a feed-forward neural network, and it's the same sort of architecture that you'll probably want to use for solving the project if you do choose to use a neural network as your function approximator. But the 5,000-foot view is just that a neural network is approximating a function. You put in an input and it spits out an output. So an input might be this vector here, -2, or I'm sorry, 0.2, 0.1, -0.2. You can think of all those as your nodes for your input layer. And then each one of the input nodes is connected to each one of the neurons in the hidden layer, and you can think of these arrows as weights. So these three arrows here are the weights associated with this hidden neuron, and it does something magical, which we'll talk about in a second, and then sends its output to the output layer, which does the same thing. It has weights represented by these arrows, and then finally it spits out a value. So here our output is 20 and -10. And so if you happen to know the actual value that you should have got for putting this into the function, so in this case I'm saying that I was expecting 20 -5, not 20 -10, you can calculate the error. So the squared error between these, it got the 20 right, but it was off by 5, so I have 0.25. Now I can use that error to update all of my weights in such a way that if I were to pass the same vector into the neural network, it would spit out something closer to the actual answer. And usually it does that by backpropagation and one of the many optimizers that you can choose. To talk about this a little more, you need to understand what a neuron is doing. So a neuron really is just a set of weights and an activation function. And it outputs, or it takes in input from the outputs of the previous layer. So for your first hidden layer, it takes in your input vector. And what it does is it multiplies each input with the corresponding weight. So negative or 0.2 times weight 1, -1 times weight 2, -2 times weight 3, and then it sums up those values to get some scalar. I call it k here, and then it applies an activation function to it. So what's an activation function? There are many different types of activation functions. Here are some common ones, but there are several more. And usually what you're trying to do with activation functions is shape your values into like some bounded range, and you also need the activation function to be differentiable because that's how backpropagation works. So just to talk about a few of these, the identity function is the same thing. If you hear someone talk about a linear activation function or having no activation function, they're really just talking about the identity, which instead of applying some f to k, you can just output k. Some other popular ones are the logistic, which is often referred to as sigmoid. It'll map all the values you put into it to an output between 0 and 1. So anytime you need your outputs to be between 0 and 1, like in a probability or something like that, that's a good one to use. Hyperbolic tangent is pretty popular. It maps -1, maps values to -1 to 1, so that can be useful. And then what's really popular right now, and what you'll see in most of the papers for this project, is the ReLU unit, and that stands for Rectified Linear Unit. But essentially all it's doing is if the sum here is greater than 0 or equal to 0, it will just map out the identity function, and then everything else it will return 0. So that's a pretty popular one and usually works good with RL. So now we can make the leap from the tabular Q-learning method to Q-learning with a neural network. So we'll start here. This is an excerpt from one of the papers, and the actual paper is in the slide notes if you want to look it up, but it's the DeepQ network paper. So a DeepQ network is a multi-layered neural network, so just like this one here, that given a state S outputs a vector of action values, which we've talked about already. And so Q, the network, is approximating a function that maps states to action values given the weights of the network, which they are representing with theta here. So I also want to point out two important ingredients of the DQN algorithm are the use of a target network and the use of experience replay. The target network with parameters theta bar is the same as the online network, except that its parameters are copied every tau steps from the online network and kept fixed for all of the other steps. So what that's saying is basically you have two copies of your network, and one of them is going to have some weights that you're going to keep constant over some amount of training steps. And then at whatever time period you choose, you will copy the weights from the network you've been training into that target network. And the reason why they developed this target network is because if you're predicting values from your next states using the network that you've been training on, the weights of that network are changing every step. So you're not getting very consistent values. So they developed this target network system in order to kind of get consistent values as you query for predictions of values, and that seems to have stabilized results. So this algorithm over here, without all the comments that I put over it, is the algorithm for Q-learning with a neural network without the target. And then I've kind of made some changes here to incorporate the target network that they're talking about. So the overview is you want to keep some sort of buffer to keep memory over the experiences that you encounter. Then you initialize your network with some random weights. You also create a target network, which I'm going to call T, and that's going to have the same weights as Q. You'll observe state S, and then you'll repeat the following. So just like with the tabular Q learning, you'll select an action epsilon greedy, so some probability it'll be random. Otherwise, you take the argmax over Q when you query it for whatever state you had, or whatever state you're at. And then you'll carry out the action, you'll get a reward, and you'll be in a new state S prime. And then you'll store that experience in memory. And then you'll also really want to store whether this was terminal or not, because that's required for the update. So add a comma and then done right there. Alright, and then in each step after you've taken action, you'll do your experience replay. So every step, not after the episode finishes, but every single step you should be doing experience replay. So you sample some random experiences from that memory. They're representing them by these double SAR S prime notation. And then you're going to calculate the target for each one of those. And I'm going to go over that a little bit more on the next slide, but essentially, if S prime is terminal, then your target equals the reward. Otherwise, your target equals the reward plus, and then this is the exact same thing as before, except now we're using that target network to query over to query our new state. So you're using the target network to predict the values of being in S prime. And that's why you're freezing those parameters. So when you're doing these predictions, you're predicting from a constant network that isn't moving, and you're not getting that instability there. So use T to get your predictions for S prime. And then you train Q using the loss, and we'll talk about that on the next slide. So you're doing this, and then every so often, every some tau number of steps, right here, you would update the weights of T by just copying over the weights of Q. So T it's following Q, but it's following Q a lot more slowly. So that's the algorithm. And then just to break down training a little bit more, so this term right here is the loss that you're trying to minimize. And so here's a little example. And this is kind of where Q learning with a neural network kind of is slightly different than a tabular methods. It can be confusing the first time you kind of mess with it. So first you get a prediction. So you query Q for the state that you're in, and you get this prediction of values. So this is what currently Q thinks taking the value is for taking each one of the 4 actions in this case. And then you calculate your target for the action that you took using your target network. So just like I talked about up here. So this line, you'll calculate the double T. And for example, that might turn out to be -3. And then to build the label that you're going to train on, you're going to set that action's that action is going to index the value of the prediction that you're updating. So if you took action 1, for example, then you're going to plug in that target that you calculated into index 1 of your prediction. Because you have no idea if these have changed because you didn't explore those actions for this experience. You just explored action 1. So you calculate your target and you update your prediction just for the action that you took. And that's your label for training. So now you can train your Q network by giving it the state that you experienced and the now updated label that you believe to be more accurate. And so what the Q network is going to do is it's going to predict what it thinks the values for this state should be, and it's probably going to be something like this, and then it's going to compare it to the label, and it's going to do that. It's going to subtract the difference here and square it, and its goal is to minimize that squared error. So it'll move the weights in such a way that if you were to query with this again, you would hopefully, or query with the state again, you would hopefully get an answer more resembling what you calculated here. And just as a note, you won't just do this for one sample at a time. You're going to want to predict all of the states in your mini batch, calculate all the targets, build all the labels, and then you'll just train over Q in one step. So it'll get the mean squared error over that entire batch. And that will help you better generalize instead of getting your weights moving around just based on one sample. So making the leap from there to double DQN actually isn't too challenging. So here's the old update rule, and it's actually equivalent to this, and I'll make that argument right now. So what is the max of t given s prime? So send in s prime to t, you get an array, a vector of action values, and you're taking the max one. So this operation here gives you the maximum value for taking the best action in state s prime. So what does this do? This looks different, but if you first query t for s prime, you get all the action values again, and argmax finds the action that produced that best value, and so querying t by s prime and using the value from that action will in fact be equivalent to this rule up here. So either way, you're getting the best value for taking the best action. And the reason why we put it in this form is because it's easier to see how the double Q learning, double deep Q learning update rule is. It's very similar, except now the only change is you let Q pick that action. So you'll pass your S prime to Q. Q will give you the list of values per action. You use argmax to pick the best one of those, and then the target value still predicts the value, or the target network still predicts the value for that S prime, but now it picks the action that Q chose. So what does this do? Well, it untangles the action selection from the value prediction. And what DeepMind found in doing this is you actually get a better estimate of the action values. Because in the old way, you're using the same function approximator to predict values as choosing actions. And so what happens is you overestimate the state action values. So detangling will normally help you better estimate, sometimes underestimate, they found in some environments, but usually it will help you more accurately estimate values. And then just an excerpt from the paper here. This version of double DQN is perhaps the minimal possible change to DQN towards double Q learning. And their goal here was to get the benefit of double Q learning, but keep it as similar to DQN as possible so they could compare them fairly. So that's why they call it double DQN. It's actually a hybrid of DQN and double Q learning, which is another algorithm. But because we're not really trying to compare them, we can just go ahead and implement double Q learning instead of double DQN. So this is the tabular version of double Q learning, and it's kind of similar to what we've seen before, except now you have two networks, or two tables, QA and QB, and when you choose your action, you actually kind of get a consensus from both of them. So you'll query Q for S, and you'll query QA for S, and you'll query QB for S, and you'll just average those values and pick the best action based on that average. And then you'll randomly choose whether you want to update A or update B. And so if you're flipping a coin each time, they'll both, in a limit, be updated an equal amount of times, and they'll kind of track simultaneously. But what happens by doing this, you can kind of ignore the tabular learning rule all you need to know is that if you pick A to update, A becomes your model that you're training, and B becomes the target network. And if you pick B, just pretend B is the model that you're updating, and A is the target network. And then you use the exact same rules as double DQN to actually train them. So here's what that looks like. So if you have networks A and B, and you have an experience tuple, double S, double A, double R, double S prime, you'll randomly pick which network to train just by a coin flip. So let's pretend that we chose A. We'll find the action denoted by A star that A would take from S prime. So that's equivalent to argmax of A queried with S prime. And then we'll update A in the same manner as DDQN. Actually should be DDQN. So in DQN, that was the update rule. Now we're updating it as if B is our target network, and we're using the action that A chose. So double Q learning is very similar to double deep Q networks, but instead of having a dedicated target network, you're actually flipping the role of the two. And this is actually the method that I implemented, and it worked out really well. So might be something worth looking into if you're having trouble. And so that's double Q learning. There's also a lot of confusion on parameter tunings and what the best way to tune them is. And there really isn't a right answer, but this is some advice that is probably pretty good method. And the biggest thing is to just start as simple as possible. So a single hidden layer, use a common optimizer like Atom, use the default learning rate for it, a common activation function like ReLU, but make sure that for the output layer you are using that linear activation function so you can accurately get values. You don't want to squash any values. For the number of neurons, generally it's best to start small, and then I like to go up in powers of 2 or maybe steps of 50. Gamma, I always think about the geometric series and how it converges. So if your maximum reward was 1, then the upper bound would be 1 over 1 minus gamma. So if gamma was 0.9, that would converge to 10. And so really you're only looking forward at most 10 steps. So I like to think about, how many steps are going to be in the episode that I'm playing, and so how high does gamma need to be to accurately capture the information from that far into the future. Epsilon, no surprise there. You want to start high and go low and decay it slowly over time. I'll pick a number of episodes, like say 1,000 for the first experiments, and I'll decay it at a rate in which I reach my minimum epsilon toward the end. So if I'm doing 1,000 episodes, I want to reach my minimum epsilon around 900 or so. And then if I see it's learning, but I need a little bit more time, I'll increase the amount of episodes, and then I will slow down my decay to let me reach out a little bit longer. For experience replay, I would just say look at some tutorials, maybe see what other people are using. When I look around online, a lot of people usually use things in the range of like 32 to 256, but really you're just trading off between better generality and speed. So a lower number is going to be faster, faster training at least, maybe not faster to the goal, but faster training. But a higher number will get you better generality. And then so if you do all that, and you still don't witness at least some amount of learning, you've probably made a mistake somewhere in your algorithm and need to go back and really debug. Otherwise, that's a good time to start tweaking parameters and get the most out of your implementation as possible. Some additional topics that I haven't really messed with too much, but they're out there, are using other function approximators. So instead of a neural network, you could use k-nearest neighbors, support vector machines, random forests, other things like that. You could also play with prioritized experience replay, which there's a really good paper on that, dueling Q networks, policy gradient methods, or actor-critic learning, which is kind of an extension of policy gradients. So there's a lot out there, but have faith. You can definitely solve the environment with just the deep Q network, although I do expect you will see better improvements as you move up the food chain, so to speak, of the various algorithms. Hope I helped a bit, and I will see you guys on Slack and Piazza.